Hi students. So today we start optimization tutorial 10. Today I am going to discuss a method which actually does not seek to find the exact minimum of the unimodal function. So these are essentially a class of methods known as the inexact line search method. We are going to particularly look at a method known as the Armijo's rule. I am Dr. Ganguly. So in today's tutorial, we are going to basically solve some simple problem using this rule. We are going to look at a numerical example for this problem, maybe do one or two steps of this method, and then we are going to write a Python code and we are going to check the Python code by comparing it with the numerical example. So if you are not familiar with this particular topic, make it a point to look at lecture 10 that essentially describes the theory behind the method, and also look at the optimization playlist for the full course. Now let's start with a very simple function which we have been considering for all the one-dimensional search problems. And what we are going to do now before we begin on this search method is that we are going to define this concept of these lines being there. And these lines can essentially be defined in this manner, that the line is f0 plus alpha into rho into f dash 0, where of course f is the value of this function or this function itself and f dash is the derivative here. So essentially we need these values at 0, and with that we can get this line here. Now let us see how these lines look like, because this line is the concept behind the Armijo's rule. So we are going to plot this line for various values of rho. So I have selected values such as 0.01 to 0.99. The value of rho is typically between 0 and 1. So that's why I have selected these values. And then we are going to plot the lines and the function. There is only going to be one plot of the function, but there are going to be several plots of the line because we are going to plot it with all these different row values. Now instead of doing it in Excel, I'm going to do this in Python. So that's going to help us figure out how to plot things in Python. Now before we begin, we can actually try to get the equation of this line. So again, the function f is given here. F0 is clearly 1, because if we set 0 values here, e to the power 0 is going to be 1. Now I can immediately calculate f dash, that's given here, and then f dash of 0 becomes negative 1, because again I have negative e to the power 0 and that's negative 1. Now once I get f0 and f dash 0, I can write the equation of the line by substituting f0 is 1 and f dash 0 is minus 1, and once I do that I get this particular equation here. So now you can see this equation is going to vary depending on the value of rho I select. Now for more details, of course, take a look at optimization lecture 10 on the Armijo's rule. So let us write a Python program to actually plot these lines. So what I have done here is that I have first defined the function. The function is of course in the form x square plus e to the power minus x. Because I use exponential, I have to import numpy in the main program. And also I need to import matplotlib.pyplot as plt. So this is the library in Python which helps us to make many nice plots. Now what I do is I create a series of points. So essentially I can do that using the linspace command, and I create these points between 0 and 1, and I create 100 of these points here. Now I also create a list of all the row values from 0.01 to 0.99, which we gave in the problem in the previous slide. Now I create a for loop that is for value in row list. So this val is a thing you can use in Python, and then what this for loop will do is that it will go through all these vals here. So I set row is val, and then I essentially calculate the equation of the line here, and then I invoke various functions which are built into Python in the matplotlib library. So essentially I plot it. So this is the x variable, this is the y variable, this is the label, and I also give X label, Y label, I give a title to the plot, I want to plot the legend, and then finally I plot this function here also. So here I was plotting the line, and now I plot the function, and then I essentially show this plot. So what's going to happen is that the function itself, that is f here, is going to be plotted, and the line, that is L here, is going to be plotted for various values of rho. So let's check this out. So this is the plot I have got here, and you can see that these are for various values of rho here. Now I have put these two here to just to show these are copied and pasted from the previous figures. So what you can see here is that the function is something like this. So as we all know, the minimum point is somewhere near 0.35. We have been checking that out for several tutorials. And now what we get in this rule is that we get all these lines here. These lines have been generated by varying the values of rho. And now you can see something which is interesting, that we can see there is a point where this line crosses this curve, and all the points below it are actually quite nice and legitimate points as far as the minimum point is concerned. So one of the things about selection of these lines is that we need to get a good value of rho. Typically a value like zero point 0.2 turns out to be quite good, and also we will see that generally the function below the line is considered good. So you can see here the function is here, the lines are here, and if the value is below, it's generally an acceptable value. But if it goes up, you may encounter some place something like this here. So this is the basic empirical concept behind which this search method is based, and we'll see how it works now with a numerical example. So let us now try to find the minimum or estimate an approximate minimum using the Armijo's rule. Now we will use these two values to essentially do this method for the first time in this question. That is, alpha is 0.2 and rho is 0.2, and we will use the line equation as given here. So what we do here is that we take the value of the line. Again, remember the line was in this form. So I can write the line as 1 minus 0.2 into alpha. And then what I do is I take alpha 0.2 and I find the line and the function value for these point. So here I get 0.96 and 0.85. Now I check if the function lies below the line. In this case it is true. So in the case of these pink expressions, you see the function is below the line. So what I now do is that I actually increase the value of the alpha here. I essentially multiply the previous value by 2. Now this method goes on by multiplying the value by 2, 3, 4 and so on. And so first we multiply by 2, so we get zero point 0.4. So I calculate L and F at 0.4. Then I do it at 0.6. So I get these numbers here. And you will see that the numbers will keep changing until you will reach a point where the function value will be more than the line value. So what you need to do is you need to select the previous point which I have made in green, which was the last point where the function value was less than the line value, and you select the alpha corresponding to that point or that case where alpha you see was zero point 0.4 here. So this is the best estimate as far as this rule is concerned, and that's what we get from this particular choice of rho and alpha. Now this method behaves differently if we select a value alpha which is pretty large. So let us try that out also. Let us try the case where alpha is 1 and rho is zero point 0.2. So in this case what we do is that we have to start with the value alpha is 1 and rho is zero point 0.2. So I first calculate the line and the function at these 2 points, or at alpha is 1 and rho is zero point 0.2, and I get line is zero point 0.8 and function is 1.368. So in this case the function is actually more than the line value. So here this particular inequality is satisfied, and what of course this means is that I have to reduce the value of the alpha, and therefore now what I need to do is I need to calculate the function on the line at all these values here. I'm going to divide the starting value here, alpha is 1, by 2, then by 3, then by 4 and so on. So I do the first case, I divide it by 2, so I get 0.5 here, And in fact, in point 0.5 itself, I see that the function value has become less than the line. So this is of course acceptable, and therefore I take this case alpha star is zero point 0.5 here, these numbers as the minimum point or as the estimated minimum point. Now you see in this method what happened in the previous case, I got zero point 0.4, in this case I'm getting zero point 0.5. These are again approximate values, they are good enough for some algorithms out there. That is why this is known as the inexact line search. We of course know that the actual minimum of this function is given as 0.351734, which is also related to the Lambert W function value at half, which I have derived in optimization tutorial 3. So if you want to get this kind of value, you have to look at some of the methods we discussed in our previous tutorials, that is the golden section method, the quadratic method, the bisection method, and so on. Now let us write a Python code to implement this method, and we are of course going to test this code with our usual function. So to write the code and make it more general, we are going to say that it's valid for any given function, and therefore we are going to write some Python function. So of course the function f is there, the function f dash is there, and the function for the line is there. So remember, the function f is of course x square plus e to the power minus x. The function which is the derivative is 2x minus e to the power minus x, and in these cases I have to bring in numpy here essentially to get the exponential function. Now for the line I need two variables, I need to bring in x and I also need to bring in rho, and then I return f0 plus this value here x into rho into f dash 0. So this is the equation of the line. Now we create this function which essentially performs most of the math which is required. Here what I do is I test these two cases. So I test the case where fa is less than the value of the line, and in that case, if this is true, then I essentially go through a series of values of that factor eta, and this is from 2, 3, 4 onwards to some max value. So I'm going to give some large number here, and then what this is going to do is that it's going to each time multiply the starting value a with this value, and then it's going to check whether the function is below the line or not. If the function is below the line, it's going to print out all these values, for example a star, the value of the function, the value of the line, else it is going to break. So the moment you encounter a situation where this is not satisfied, you will break out, and the previous value is going to be stored or printed out as a star. Now the second situation happens when the function value is greater than L, and this often happens if the alpha value is pretty large. So in that case, what we will of course do is again we will go through that loop 2, 3, 4 and so on, but we are now going to get a star as a divided by the eta values 2, 3, 4. So the first value will be 2, next will be 3 and so on. So essentially we are shrinking this a star, and in each case we are going to print the values of a star, the function value and the line value. And if we encounter the situation where the function value becomes lower than the line value, at that instant itself we break out of this particular statement. So that's something to keep in mind. So now let us look at the some of the output we have obtained. So in this case, for example, alpha is 0.2 and zero point 0.2. I have obtained the solution as zero point 0.4 here. So I am printing out essentially a star here as zero point 0.4. This is the function value and this is the line value here. So you see the function value is lower than the line value. And I think you can check these numbers with the numerical example we have done also. In the second case, when we start with alpha is 0.1, rho is 0.2, here I have these numbers here, then what happens is that I essentially get 0.5 as the solution. So that's the solution here, alpha star is 0.5. So in this case, you see how this method works. Though in this case the function value is less than the line value, what you keep doing is that you keep adjusting the value till the last point at which this holds is satisfied, and the last point is 0.5 in this case. Now let us look at the case where alpha is 1. So this was the case where the value was pretty large. So we were essentially looking at that example 3 which we discussed before. So what happens here is that you essentially get zero point 0.5 as the answer, and the moment you essentially declare eta to be 2, you get that point here, and that's the point here. And of course here the function value is less than the line value. Finally, we can have a case, for example, alpha is 5 and rho is zero point 0.2. Just ran that to check out things. And you can see here it goes like this. So it divides this 5 as 2.5 and so on like that. And then it actually settles into a solution of 0.55 here, at which point you see the function value is less than the line value. So this is something which will happen. In each case, of course, you are getting different results. They are not the 0.3517 which you would be expecting in an exact line search. So you get some number. Generally, it is a good number. The function value is of course lower than the line value, and hopefully it is also going to reduce the function compared to the value at f of 0. So that was the Armijo's rule tutorial. It's a useful method in certain cases. Now we are done with all these methods which focused on calculating alpha k. So if you remember one of our previous lectures and tutorials, the next point in direct search in optimization, that is xk plus 1, can be obtained by xk plus alpha k into dk. dk is the search direction. So in future tutorials, we are going to look at all the different methods to calculate dk, such as those based on the gradient and so on. And we now have the Python code for this method also. There are some methods for calculating dk which are okay with the inexact line search, but there are methods which need exact line search, for example, some of the conjugate gradient method. Now, if you look at the derivation of any method, you will see in some methods the line search criteria is used in the derivation. So wherever that line search criteria is used, it means that the accuracy of the line search has to be very good. And so in those cases, you may want to use the exact line search, such as golden section, quadratic, and converge to quite a few number of decimal places. Now in this method, I showed you some very simple examples, but of course you realize that this method can be coded in or improved by trying it out with different values of alpha and rho, and then selecting the best value depending on the value of the function. So you can actually run this for several values of alpha and rho in some for loops, for example, and then what you can do is that the value where the function is the minimum, you can take that value also. That's going to be a better inexact line search than the simple one we showed you here. But the concept is of course very simple. There is a line, there is a function, and you have to find the locations where they are cutting, and then that probably is going to help you figure out what is the good solution to the problem. So again, make it a point to listen to optimization lecture 10 on the theory behind this method, and also look at the optimization playlist for more videos. Now in the playlist I have separate videos for lectures and tutorials, so I may not have all the tutorials done yet, but I am slowly building up the tutorial database also. And also, if you are not very good in math, make it a point to look at the Math Mania playlist, which is simply a selection of solved problems. It's like a tutorial, and it's going to certainly help you improve your math. And I will see you on my next video on gradients. So then we will start getting into the gradient based methods.